is R is greater than R plus, block 2, where R plus arises from the quadratic in R appearing in the metric. Okay, and these are all open subsets of R cross S2 minus sigma, and sigma is nothing other than the ring singularity. Good. Of course, block 1 and 2 are just R cross S2. So if we look at the metric, d theta is always space-like. dr is space-like on 1 and 3, but it oscillates. It's time-like in region 2. Then d phi is space-like for r is greater than 0, but on 3 its character changes. And this will be the cause of closed time-like curves, which we'll see, though it's space-like when r is very much less than 1. Minus 1, sorry. And then dt is time-like as you'd expect outside the black hole. So it's also time-like for r is less than 0, but it's space-like on region 2. And it varies in regions 1 and 3. Okay, so that's the root of all the strange and wonderful properties of Kerr to some extent. Okay, now let me remind you of the beautiful diagram we drew last time, which is, in my mind, the quintessential diagram at issue here. Okay, it's rather complicated, very ornate. And then these regions here. Okay. Okay, so now I'm going to use thick red to shade in this region. So I'll explain to you what the shaded region is in just a second. Okay. So let's remind ourselves, this is block 1. This is block number 2 between R plus and R minus. So this is block number 2. Then block 3 is everything inside here. So let me draw it like this. This is block 3, right? Block 3. And of course, the ring singularities inside and so on, but we're not going to draw that quite yet. And so the shaded region is where dt is space-like. So I told you it oscillates, and now I'm drawing to you exactly where it's space-like. Okay. Now, on the basis of this diagram, right, that I'm drawing here, we can in fact prove, right, we can in fact prove that, so this is proposition, we're not going to go through the proof, it's not too hard, that region 1 and 2 are causal. And that means there's no closed causal curves. Okay, and the proof sketch is just a sketch. But basically, in one, so you could do the proof individually for regions 1 and 2, but in one, T equals T0 is a space-like hypersurface, right? You can see that by taking the metric and restricting to a T equals 0 slice. And you can show this using, so hypersurface, you can show this. This is easy to show. And then, so that's step 1, if you like, and then step 2, any non-space-like curve, right? Any non-space-like curve, say alpha from some S to I, this is region 1, is monotonic in T, right? Monotonic in T, and therefore there's no closed causal curve. Okay, so that's quite easy to show. And you just look at the metric and the basis that's formed by the vectors that are emitted by fixing T equals constant slice. So that's region 1. And then a similar, what's interesting about this actually is that a similar proof sketch, so let me remind you, a similar proof works for region 2, but you know, those who are sufficiently awake amongst you will suddenly realize, but wait a minute, you just told me that dt is space-like in this shaded region, which definitely intersects region 2. So what's going on? Well, it turns out the proof admits a kind of mirror counterpart where dr changes itself for dt. Now, dr becomes time-like, dt becomes space-like, and by switching the proof around, but with a hypersurface of constant r, you can make the same arguments work, and you can prove eventually that region 2 is causal. So that's already something quite non-trivial that's happening. Okay, now.
So del R and del T switching is just the usual inversion of space and time inside.
Yes, yes. Now, here's an observation, right? This is an observation. D phi integral curves, right, are closed curves, right, circling the axis of rotation. I haven't said they're closed time-like curve, and in fact, they're not, because d phi is not everywhere time-like in region 3. But what this is to say is that if I zoom in onto our diagram, okay, so this is now r equals r minus, so I'm quite deep in the black hole at this point. This is r equals 0. Then my ring singularity is, of course, the locus where r equals 0 and cosine theta equals 0. So theta equals pi over 2. My axis of symmetry is like this. And what I'm saying is that the integral curves of this vector are simply closed curves that circle the axis of rotation. So you could write such a curve as follows. This will be such an integral curve. Okay.
So Martin,
yeah.
When you write things like r equals r minus,
yeah,
is that r minus of theta? It's a function of theta?
No.
Is it the hourglass shape?
No.
Or it's actually the field?
No. It's something that arises from the quadratic that we saw in the Boyle-Lindquist form from before.
Okay.
So if you remember like lecture 1 or mini series 1, let's go all the way back up. we had this polynomial that appeared in the metric. Remember, we had things like this. Let me show you. Where did I write it down? Here we go. We had this quadratic, right? R plus and R minus is simply the roots of this quadratic when the constants are arranged so that you do in fact have two roots. But remember that you shouldn't think of them as spheres, right? Because they're squashed by the rotation. Topologically, they're spheres, but geometrically, they're not a round sphere.
So in Boyle-Lindquist coordinates,
Yeah.
is this guy a sphere?
Yeah.
Constant R, and
Yeah.
it's not the same as your hourglass surface.
Well, okay, so you need to distinguish here between what do you mean by a sphere and what do you mean by an hourglass, because this is topologically a sphere.
No, that's fine. You've drawn a diagram in which you've made a distinction between something you call R minus,
Yeah,
and then something you've shaded, which is not circular in shape.
exactly, yes.
So,
But it's only circular in shape because I'm writing R equals R minus, whereas this hourglass varies in theta. But if what I just want you to be aware of, and I'm sure you already know this, but that if I computed the intrinsic geometry of the R equals R minus surface, I wouldn't have a round metric. But that's you're okay with that.
But there's
Good.
no surfaces of one. That's all I'm trying to.
Yeah, then we're on the same page.
Are we?
Say?
Are we? Because I'm
Yeah.
still confused. I mean,
No.
you're drawing multiple surfaces.
Yes.
And let's go to your beautiful diagram.
Yeah.
No, those are where you shaded.
Yeah.
Okay, so you've got an R minus, which is the black circle,
Yes.
and then you've got a dashed line,
Yes.
which is the inner edge of your shaded area.
Yes.
So what's the distinction between the two? They're not the same, right?
No.
Okay.
Yeah, the shaded region is what I wrote here. So it's the delineating in this diagram where dt is space-like. That's the red region. The hourglass is simply the boundary of that region. So when you compute where dt is space-like, there's a variation in theta. This is precisely what's being drawn here with respect to the constant R surfaces, which are drawn as spheres.
Okay. I missed this. Okay.
Oh, beautiful. No, thank you for the clarification. This is, everybody's got to walk hand in hand here. Okay, so good. So we have these d phi that are integral curve, closed curves circling the axis of rotation. And then some of you might say, well, are we done then? Are these the closed time-like curves that I've heard so much about? The answer is no, because I haven't told you what the time-like or space-like or null character of these curves might be. So to construct the closed time-like curves, which will hopefully fill all of our hearts with wonder, we have to work a little harder. So let me introduce some definitions. Okay, I'm going to call big tau the region in which the phi component of the metric is time-like. And I'm going to call this time machine. Time machine. You'll see why I'm calling it a time machine for now. Now, on the basis of this, on the basis of the metric in region 3, I can prove that 3 is vicious. Right? Now you're going to say, okay, well, what does vicious mean? Now, vicious means the following thing. For any p q, there exists a time-like curve p to q. You'll say, okay, well, why is that so strange? Well, of course, it's extremely strange because, of course, if p and q seem to be space-like separated, then this is somehow saying that I can draw a future-directed time-like curve, which somehow ends up here, right? So somehow there are closed curves, closed time-like curves going around, because of course I can take P and Q to be the same point. Right? And then I have a closed time-like curve. Beautiful. So block 3 is vicious. And vicious means it's stronger than just the existence of a closed time-like curve. Vicious means there passes a closed time-like curve through every point. Okay, that's the distinction. It's quite remarkable. Let's pause for a second just to appreciate that. Okay.
To every point in region 3.
Yeah. Exactly.
And just to remind myself, region 3 is R less than R minus.
Good. Yes.
Not inside the shaded region.
Yes, yes. The shaded region was simply to tell you where dt was space-like.
Okay. So inside this constant R sphere, R minus, everywhere there is a closed time.
Exactly.
Good. Okay.
Martin, is it correct then that on the surface, R equals R minus, stable causality is violated?
It's worse than that, my friend. Strong causality fails.
Ooh, yeah, you're right.
Okay, so I'm going to give you, because right now I've cheated you. I've told you this weird and wonderful property, but I haven't justified it to you. So I'm going to make as best I can an effort to do so in the time given without giving you a full proof, which would take us too long. And for this, I'm going to have to draw a number of pictures. Okay. So remember our definition of big tau. Big tau was where G phi phi is time-like, with negative, if you like. But that doesn't cover the whole of region 3. And so if I go closer, if I inspect region 3 a little closer, what I find is the following. This is R equals R minus. This is R equals 0. And then less than that is R is negative. And then I'm going to draw our favorite ring singularity, which goes around the locus of theta pi over 2 and R equals 0. And what you end up seeing is that in order for a curve to be closed, what you do is you have to enter a region. Let me draw in a different color. Now, this diagram will be my most challenging diagram of the day. This is quite a difficult diagram to draw, I must admit. Yeah, it's a donut whose outer equator is punctured by the ring singularity. So let me try and draw it. Let me. Yes. Yes, but only in one equator. So the inner equator isn't split, right? So it's just a usual donut. Take a scalpel, just go around the donut. An incision only in the outer edge. Do nothing to the interior edge, the interior equator. Okay, so let me try again. Let me try again with this diagram. It's quite something. Okay, so maybe I need to draw my ring singularity a bit bigger. I'm drawing this because I want to show you exactly how you construct these closed time-like curves. I don't want to cheat you and just tell you they exist. There we go. That's going to be better. Marvelous. Okay.
Those are cross sections of the donuts.
Yes. Okay. So in order for me to, let me pause on this diagram for a second. We'll come back to it in just a second, but let me introduce another diagram to you. I warned you there would be an abundance of diagrams, so I'm certainly, at least on that point, I'm not cheating you. This is P, and this is Q. And then what happens is that at this point, I intersect, I go into big tau. Okay. Once I'm in big tau, I spiral down, just like the kinds of games you see in a fair. Right. I exploit this region. I'm leaving big tau. Okay. So what have I drawn here? So let's go back to our diagram. So the blue line is the boundary of a solid torus whose outer equator has been excised. And it's the region in which G5 phi is time-like, is negative. Okay. Now, what I've drawn on the next page, P and Q, are just 2 points, any 2 points, P and Q. P and Q. Okay. The point is that you want the time coordinate as you leave P and you go into the future, the time coordinate goes up, right? The time coordinate along a future directed time-like curve goes up. But you want to bring it to Q and eventually join them up with a curve to get a closed time-like curve. And so the time coordinate here must be less than that which you started with. So let's take this t equals 0. This must be t minus some delta, right? The time coordinate must be less, because in that dotted line, I can draw a future directed time-like curve, which will increase the time coordinate. So how do I do that? By moving the time coordinate forwards? Well, what happens is that I have to go into this region, right? I have to go and pierce the donut. Okay, this is where I enter big tau. When I pierce the donut, my time coordinate will start running in the opposite direction. Okay. This is exactly what's happening, right? As I've pierced the donut, right? I'm into big tau now. And what you can show is that for a curve that remains within the donut, I can basically move my time coordinate as much as I want into the past.
But Martin, this is irrespective of where you go through the donut, because if you go through the excised part, is a problem, right?
Yeah, so you can't go to the excised part. You have to avoid the excised part, but that's not such a big deal. I mean, if I gave you a donut and I just drew a line on the outer equator, you're very welcome to find any other point to pierce the donut without hitting that outer equator.
You don't want to touch that because it's the ring singularity.
Yeah.
That's right.
Yeah. So if we drew a movie, if we somehow managed to draw a movie, what we really have in mind, right, is a kind of frame by frame movie of what's going on.
So you go forwards in time until you pierce the donut, then you go backwards in time, then you start going forwards in time once you leave the donut.
Yeah. So here your time parameter has gone from, is now t plus delta. Then you travel however long you need, so that when you leave the donut, your time coordinate is now, say, minus delta. And then this part is, roughly delta. And so you can balance out and maybe it's, maybe less, a little bit less than delta. Maybe in size, it's something like, delta, maybe minus epsilon. And then you carry over the epsilon. And then you've got a time parameter that's come back to its usual self.
There are no restrictions on the path length other than the fact that you don't pass through.
Oh yeah. As to yeah, exactly. Yeah. So you must, the only chance you have of going back in time is to exploit the donut, because the donut is the region in which G phi phi is negative. But you can spend as much time in the donut as you can to try and change your time coordinate backwards as far as you can, so that you can eventually come back to where you were. But the point that I'm making by doing this and by emphasizing so strongly on this donut is that it's exactly how the closed time-like curves arrive in the Kerr interior. They don't just arise out of nowhere. They arise by exploiting the donut. Right? The donut is your time machine to some extent.
So Martin.
Yeah.
You've shown that such paths exist.
Yeah.
Great. Are these actual geodesics?
No.
No. So you need a rocket or something.
Yes.
To follow the path.
Yes. Yeah.
In fact, I was just about to ask what a very closely related question to what Ramesh asked. So yeah, not only are these not geodesics, it looks like in fact you're going to need some pretty wild acceleration to follow these curves. Are there Gödel's there are these two papers by Malum and some other people, very elegant, that compute lower bounds on the acceleration that's needed to traverse any closed curve whatsoever, time-like closed curve whatsoever in Gödel space-time. Do you know, are there any such comparable estimates in Kerr? Is it always the case that you have to expend, so in Gödel space-time, you have to expend an extraordinary amount of energy to traverse any closed time-like curve whatsoever? Are there such lower bounds in Kerr, or can you in fact arrange it that you can expend very, very little energy and still traverse a closed time-like curve? I suspect that is pretty high level.
I think the answer will depend on where P and Q are to begin with. And my thought is that actually traveling along an integral curve of d phi is close to being a geodesic. So actually you won't have such trouble. But so I would expect, naively, I would expect that you can compute such lower bounds, but naively I would expect those lower bounds to be far better than their Gödel counterparts. The reason being that once you're in the donut region, you're kind of just following d phi. Now, there is a caveat to that, of course, because if you get too close to the ring, you're going to be in trouble. So you're going to have to stay far away from the ring, and that'll depend on what parameters you enter the donut, right? If you enter the donut close to the ring, you're going to need an extraordinary acceleration to avoid it. But perhaps if we think of a trajectory that isn't flying in like this one, say, but that's flying in like something like this into the donut, right, which will become, you know, to create such trajectories, you're already going to be accelerating, and it's obviously going to be something already non-trivial. But once you're flying in at this angle, if you like, with respect to the donut, I can believe that following d phi is not going to be as much as it is in the Gödel's examples, but this is a good computation someone ought to do. Yeah.
It's a great question. You can answer it, you should.
Yeah. No, I think it is a good question. I think it's doable. I think it's quite, it should be straightforward to do.
Mhm.
Yeah.
But
I
going
haven't-
on d5 itself is not a geodesic, right?
No,
So going to need some.
it's going to need something, but yeah, it's going to need something for sure. But no, it's a good computation. It's a good computation to do. It's a good computation to do.
Nice question, Rick.
Yeah, very good question. Okay, so what you end up proving, by the way, is that you can show that the time machine right lives in this region, right, and this is precisely the thickness of your donut, right? Thickness of donut. Okay. Good. Now, it's about 35 minutes past. I want to talk about the topology of the interior, and that I should leave about 10 to 12 minutes for that. But I also want to justify myself to you a little more than I have done with respect to this business. So let's be a little more detailed. And I will try to do these computations relatively quickly. Because I think it's worth it for you to see just how these functions, which you've seen in endless talks given by many speakers, that you see actually just what they imply. All right, so this guy, the sign of this guy is obviously going to be controlled by this guy because this is positive. So that's just what I'm writing here. And so we can just write this f of r theta, if you will, just by expanding out what I just wrote. So let me just do that right away. Okay, so this is what determines. So this is going to be space-like, or r is positive, because every term in this equation is positive, right? It's just a bunch of quadratics and quartics. So that's observation 1. Observation 2, take theta equals pi over 2. So we're probing the equatorial plane. Then in fact, f of r theta becomes r times r cubed plus a squared r plus 2m a squared. And if you just remind yourself of your high school days and you want to plot this, you will quickly realize, computing derivatives, etc., that this guy looks like the following. Let me write it underneath. This guy is going to look like this. So there's not going to be any stationary points. You can see this quite easily. Okay, and then because we are multiplying by r, the effect of that will be to turn the curve into something like this. right? You know it has a zero at R, you know it crosses the y-axis at x equals 0 because there's a coefficient here of R. And so the bit where it will be negative is precisely when R is between k and 0, where k is the root, k is the unique root of this fella. Okay, and then you'll see that now f in this region will be negative. Okay, so that's probing the equatorial plane, but that's not quite the donut I promised you. So let me now show you the donut. This, we fully expand it, looks like the following. I'm going to just write it again, but now I'm going to expand it in terms of C by just changing and using the standard trig identity. When I do this, I have a function in f of R and C, and I can just plot this in the RC plane. Okay, I can just do that. And then I'd like to see where this changes sign. So where is the 0? But now, and this is perhaps, you know, something very neat here that's about to happen. Remind yourself of these kinds of equations. Right, this is a circle that's located at x0, y0, right? And whose radius is a. But now observe that the terms we have here are, right, quartic, and there's a quadratic term. I can put this minus, I can put it inside a bracket, and then there will be a constant term that there is no constant term, which means that I must be canceling in my R bracket and my C bracket, which means that this actually plots in the RC plane. The 0 locus of this polynomial is nothing other than an oval, right? In the RC plane. And this, my friends, is the origin of the donut. Because that's when we have a change of sign in G5I. Okay, so at this point, so I'm gonna leave this. I must apologize. I very quickly run to the bathroom and be right back.
So what are the parameters of the polynomial physically? A,
Here's the spin.
A is the spin.
Yeah, here's the mass.
And C?
C, I'm not quite sure what he's talking about. Eric, what is C?
C is just a fiduciary constant that's keeping track of a combination of R and theta. I think it's like something like R squared sine theta plus something that just appears constantly throughout the Boyer-Lindquist expression.
Okay.
I can't remember the exact expression, but it includes C squared, and it includes sine theta, includes sine theta.
Good. So C is allowing us to explore the theta part of the space.
Exactly.
Okay, fine.
And A isn't A is actually the spin per unit mass, not the total spin.
Mhm.
how do you get the inner radius of the donut?
You don't get it from this, right? That's just the R.
How you put the-
Apologies for the time.
He was just asking how you get the inner radius.
of the donut from that?
Yes, beautiful. Let me get to that. So let's go back to probing the donut at the equatorial plane.
Can you please repeat the question that was just asked? It was difficult for at least for me to hear.
The question was, why is it that, how do you find out where the donut ends, where the inner equator of the donut is? So when you probe the donut in the equatorial plane, you want to show, you get this for f of r theta, and when r is very negative, then the quartic term in this will dominate. It will be positive. So you know that for very negative values of r, you're in the positive part, and so g5 phi will be positive. And so it's just about finding where the unique root is of this. That'll tell you where, smaller to r equals 0, where you're changing sign. But that is just determined by the unique root of this equation. And now it's just a cubic equation, and you just have to find the root of this equation. So that's no real trouble, which you can do from, either using a computer or trying to do some clever manipulations, however you like to do it. It's nice to see, of course. Let me show you why the donut, it could have been that this is different, right? But it turns out that, if I just differentiate this in R, what do I get? Let me use a different color to be less confusing. If I differentiate this in R, I get just the cubic, I get the following. But then I can see that there's no real solution. So there's no stationary point. If there was a stationary point, then this would be changing signs, right? And if that would be changing signs, then when I multiply it with the R at front, the regions where it's positive would become negative, and the regions where it's negative would become positive, and vice versa, which would mean that I wouldn't get a donut, right? But I'd get maybe a succession of donuts, right? I would get a succession of donuts. Get an outer donut and an inner donut, but that doesn't happen. That just doesn't happen. But if there was a different term here, if this was a negative, for instance, then that would happen. So it really is a fact about the Kerr metric. Okay, so now we're going to talk about topology, just because it's so beautiful and ornate. But I don't have that much time, so I'm going to have to be fairly quick. Okay, so an important notion: if I have a topological space, all right, this is a topological space, which means it's a space endowed with a topology. This is a subset in a topological space. Okay, then what's called a strong deformation retraction, okay, is a continuous map from X to A. So there's a continuous map, right? Such that rho of A is just A, but right, for all A.
Martin, when you say it's continuous, are you giving A the subspace topology? So does A actually have to be a subspace, not a subset? Or what is the topology on A with respect to which the map is continuous?
Yes, subspace, sorry. And then there's I'm thinking of the subspace topology here, yeah. So, so eventually, so this doesn't move, but then, so the point being that I'm retracting something onto something else. So say this is X, which is just the real line, and then say that A is just a point. Okay, then I can just take a continuous map, which maps everything to the point. Right, and that's a continuous map. I can do this in a continuous way. And this is called a retraction for obvious reasons. And a strong deformation retraction, so this is a retraction, so is when you have this, so 1 and 2, right, 2, this is homotopic to the identity, right? And so a great example is the sphere, so Sn in Rn plus 1, where I take Rn plus 1 minus the origin. So this point is excised, and then I take every point and I flow it to the the boundary. And if you want a precise homotopy, so that's a continuous map, I can give you the following homotopy. Right, and this is H of X in S is continuous in S. S equals 0 is the identity map. Okay, and S equals 1 is X. Sorry, is X over X, which will just map it to the sphere,
Superscript N.
the N sphere,
Sorry?
the N sphere. So the point here, you should really think of just flowing to a sphere from the outer part of the sphere and flowing onto the sphere from the inner part of the sphere. But then you'll say, okay, but what happens to the origin? Well, I've excised the origin. And what that means is that the following spaces are, the following spaces are, right, if X1 is a retraction of X2, then X1 and X2 are homotopy equivalent, right? And homotopy equivalent is the most basic and important equivalence in topology. So basically, with respect to topology, these spaces are the same. They're just a deformation of one another, continuous deformation. So using this language, let's get to Kerr. So remember, this now is going to be my second favorite, or maybe my favorite diagram as well. One of my favorite diagrams.
Martin, I just want to be clear. The example you gave of Sn and Rn plus 1, that was not a strong deformation retraction.
It actually was. It was.
Well, then I think I misunderstood. I thought you said a strong
minus the origin. Minus the origin.
So, but in a strong deformation retraction, doesn't everything outside the subspace go to a single point in the subspace? That wasn't what happened with Rn plus 1 and the N sphere.
No.
That's you say R of X equals A for all of X in X, and R of A equals A.
Sorry. That was a typo.
Okay, thank you.
It was a typo. Sorry. So thank you for pointing out the typo. Thank you, Eric. So let's do this. So in blocks 1, so remember the blocks 1 and 2 are just R2 cross S2. So R I can contract to a point twice. So this is just homotopy equivalent to S2, right? So the topology of 1 and 2 regions 2 is just the topology of S2. But here's what happens in the interior, and this is remarkable. Right, so wait a second. Shouldn't have drawn it like this. Okay. I'm going to draw my usual diagram, but I'm going to ignore the r equals 0 sphere, and I'm just going to draw the ring singularity. But then I'm going to draw an inner sphere, right? Okay. And then notice that I can contract all these to this S2, just like I did with Rn plus 1 minus the origin and Sn. So I can homotope all these points to this S2. So let's call this S1. And then what I can do, and this is slightly harder to see, but if I consider this solid torus, right, then I can homotope this to this outer S2, which is S1 in my language. But then notice what will happen to these points. They will go and they will be stopped because I'm approaching it from the other side as well. This is one of my favorite diagrams, maybe in the whole of the Kerr industry. So you see what's going on here. The boundary of a curve which threads the ring singularity, so namely the curve, not the boundary of the curve, just the curve, is being homotoped to part of the outer two sphere, part of the inner two sphere, and a meeting point. And so the homotopy type of the interior of block 3 is none other than the linking of two spheres via their north and south poles. This is the topology of the interior of Kerr, where one has in mind that the ring singularity is doing something like this, right? And then if I were to draw a closed curve that generates an element of the fundamental group, it'll be a closed curve traveling that threads the ring singularity. Okay? And this blue curve is none other than a curve that goes like this. Right? Because remember what's going on. This is being homotoped and it's going to hit part of this. This is going to hit part of this. This is going to hit part of this. And this is going to hit part of this. And so when we take this blue curve out, it looks exactly like this blue curve that I've drawn here. So the homotopy type of the interior of Kerr is nothing other than the linking of two spheres.
I thought we had an excision, right? So what happens if that part of the donut that we cut out?
That's not part of the space. It's a singularity. It's not part of the space.
Okay.
Yeah. I'm abstracting away from the geometry in the space, and I'm giving you just what's the topology of the inside.
What are the two? I really want to understand this diagram, the antecedent diagram to this one.
Yeah. This one. This
I
is,
haven't
yeah, this is a beautiful
quite got
diagram.
it, and we're at
Yeah.
T - 3 minutes.
Yeah.
So we may have to come back to this. but
Yes.
What corresponds to the two spheres that you're? that
So
show in the-
You
in the
you should think of,
substrate?
okay, so you should think of, okay. Remember what I showed you here. I showed you here, I took Euclidean space, I got rid of the origin, and I showed you how to continuously deform it onto the sphere. So you should think of a big space topologically as just being the sphere. Okay. The same thing is happening here, except that rather than removing a point, I'm removing a ring. And I'm doing the same procedure. I'm looking for a deformation retraction that does the same thing as what it does here, except that now it's more complicated because I haven't just removed a point, I've removed a ring.
So this is the analog to that thing that you learn in elementary mathematics where you map a sphere with a puncture at the top to the plane.
Yeah, that's different.
That's it.
Yeah. That's just that's called projective space. It's a different thing used for different things.
So show me again, I'm sorry.
So yeah, so the point is to continuously map all the points in one space onto the other. In this case, it's origin, it's a Euclidean space minus the origin onto the sphere. And then I'm doing the same thing here, but because I'm removing a ring, think of now don't think of the donut whose outer equator is the ring. Think of a donut whose inner circle inside the actual solid part of the donut is the ring singularity. So I'm hugging the ring singularity with a tube, just like a bicycle tube. And this is exactly this black curve here, right? This is exactly this one, right? This is the tube going around the ring singularity. And then I'm deforming everything around that ring singularity onto something else. And what I end up with is deforming it partly on this and partly on this. You see how topologically those are the same. One is a tube and one is a tube, but that's kind of been expanded in different directions. And then I do this from all directions around the ring. And what that produces is exactly this picture, namely two spheres that are linked, meaning there is a connection, there is a path from their north poles to their south poles. Well, from the respective north poles to the respective south poles. So topologically, the interior of the Kerr block 3 is exactly this. That's the topology of the interior. And of course, one can go a step more, and I'm going to make you dizzy now, and I apologize, but one can think about the universal